All right, so on our first theorem of the chapter, we're going to take a finite normal extension. Now, when you read finite normal extension in your mind, you should be thinking immediately this is a splitting field. It's obtained, L is obtained from K by adjoining all of the roots of some polynomial over K. Right? We proved that equivalence when we were talking about um, uh, normality. Okay, so suppose you have such a thing, and you have an intermediate field. So M here is some intermediate field. And you have a K-monomorphism from M to L. There is one given one, since M is a subfield of L, we can just sort of include M into L. But maybe you have some other K-monomorphism in mind. So you have any K-monomorphism from M to L, and I'll give you an example of this after we prove this. Then there exists a K-automorphism, sigma of L, such that sigma restricted to M is tau. I like to think about this with a diagram. So we have M mapping to L via tau, and the image of tau, so we have K also as sort of a subset of M. The image of M under tau is going to be some other subfield of L. So we can think about that image tau as just tau of M, right? That includes into L. So I'll do a hook to mean includes. And then tau is also this mapping here. It's the guy that sends M to tau of M. Tau being a K monomorphism of M into L says that, well, K should be a subfield here as well, and K fixes tau. So this is like the identity map, if we like. What this theorem says is that we have an isomorphism tau between two subfields of L, M and tau of M, right? Because we can identify M, well, tau is going to be an isomorphism onto its image. Any field monomorphism is an isomorphism onto its image. What this is saying is you can extend, let me do it in blue, you can extend to some sigma such that the diagram commutes. Now, if that's not helpful, if diagrams commuting isn't helpful, that's fine. If it is, this is what it's saying. We can find it. So there exists a sigma that makes it commute. Now, existence is not existence and uniqueness in this case. In general, there may be lots of different sigmas that make it commute. Okay, so we know there exists at least one. So how might this be helpful? Let's actually do an example before we do the proof, because I think an example will help. All right, let's see. What color do I use for my examples? Here we go. All right, let's go back to this Q adjoint alpha from before. And let's consider F is T cubed minus 2. Then the splitting field of F is, we've done this before, we need to have access to the cube root of 2, and we need to have access to omega. Okay? All right, so inside of sigma of F, there's many subfields. I know, for example, that there's at least two. There's Q adjoint alpha is a subfield, but also Q adjoint omega alpha is a subfield. So these are both subfields of this sigma F. Great. There exists a mapping tau here that takes alpha to omega alpha. Right? This is just the isomorphism from Q adjoint alpha to Q adjoint omega alpha that you did in the very first homework and that we've seen again and again and again and again. I'm just saying do that isomorphism, then include into sigma F. So that's a Q monomorphism. So this tau is a Q monomorphism because that tau we saw in the first video fixes Q. And we can identify, to complete this picture, the image of tau with Q adjoint omega alpha, and we can include that in a sigma F. And what the theorem is telling us, I've already used blue, huh? Let me use orange. The theorem is telling us is there exists an automorphism of this field sigma that extends tau. So theorem says there exists sigma from sigma F to sigma F, a Q automorphism extending tau. Now, what are Q automorphisms? They're elements of the Galois group. So keep in mind sigma f is a 6-dimensional Q vector space. What we've done is we've used this theorem to come up with an automorphism without actually doing a whole lot of work. We just had to check that tau was an automorphism, but tau is a monomorphism, but tau is an isomorphism between these guys because of minimal polynomial arguments. So the fact that tau is a monomorphism, this guy, is no work at all. And by using the theorem, we get that it extends to an automorphism here using no work at all. So this is helpful. What are we learning? This is helpful to construct elements of the Galois group. We constructed a sigma by doing nothing. And what do we know about the sigma? We know the sigma sends alpha to omega alpha. This is great. This is fantastic. So that's an example of how it's useful. Let's prove the theorem real quick. Well, we know that normal. I'm gonna do a little bit of scratch work in the interest of time, but write better than I'm about to write. Normal plus finite is equivalent to splitting field. So L is some sigma f for a polynomial, maybe not irreducible, doesn't need to be reducible, f over k. But k is contained in M is contained in L. So by one of the homework problems from the splitting field section, L is a splitting field for the same polynomial, f over M. And since tau maps M into L, it is also a splitting field for tau of f over tau of M. All right. But tau restricted to k is the identity because tau is a K-monomorphism. So tau of f is just itself, right? All the coefficients of f are in k, and tau fixes k. So when we change coefficients, we don't actually change anything. All right, great. So what do we have here? We have the theorem from in chapter 9 that we have a isomorphism from M onto whatever its image field is. And sigma is a splitting field for f, which is also tau of f, over both M and tau of M. We proved in chapter 9, and we proved in chapter 9 that when we have this scenario, there exists a sigma from the splitting field of M of f over M to the splitting field sigma prime of tau of f over tau of M, the image of f under tau. But the polynomial f is the same, so sigma and sigma prime are the same thing. And this is an isomorphism. This was proved in chapter 9. I encourage you to go back and look at it. All right, and I think that's all we wanted to do. And oh yeah, and sorry, in chapter 9, such that sigma restricted to tau is sigma restricted to m is tau. And since tau restricted to k is the identity, sigma also restricts to k to be the identity, and so sigma is a k automorphism.